Right, in 8.1, we're going to talk about sequences in series. So 8.1 is kind of an introduction to sequences in series. In 8.2 and 8.3, we're going to get a little bit more specific on types of sequences. But for 8.1, it's kind of just a broad idea, an introduction to sequences. So we've got two different types of sequences. An infinite sequence goes on forever, so it does not end. So it goes to infinity. Typically in an infinite sequence, we would see like a dot, 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 meaning that it just keeps on going. The other type we have is a finite sequence, which means that it has an ending. An example of a sequence is something like 2, 4, 6, 8, dot, dot, dot would make it an infinite sequence. In example 1, we're going to write the first 4 terms of each sequence. So for A, it gives us the sequence of A sub n is equal to 3n minus 2. So I want to find the first term, which is A sub 1. So that just means I'm going to plug 1 into my n. So we have 3 times 1 minus 2. 3 times 1 minus 2 would be 1. Great job, guys. Next, we're going to plug in 2. 3 times 2 minus 2. 3 times 2 would be 6. Minus 2 is 4. For our third term, we're going to plug in 3. So 3 times 3 minus 2. 3 times 3 is 9. Minus 2 is 7. Then our fourth term, A sub 4, would be 3 times 4 minus 2. 3 times 4 is 12. Minus 2 would be 10. So these would be our first 4 terms. We have 1, 4, 7, and 10. Let's do the same thing for B. So I want to find my first term, A sub 1. I'm going to plug in 1 into my n. So we have 3 plus negative 1 to the power of 1. Negative 1 to the power of 1 would be negative 1. So 3 minus 1 would be 2. We plug in 2. We have 3 plus negative 1 to the power of 2. What's negative 1 to the power of 2? Positive 1. So 3 plus 1 would be 4. Then our third term, we plug in 3. So 3 plus negative 1 to the power of 3. What's negative 1 to the power of 3? Negative 1. So 3 minus 1 would be 2. And then our fourth term, we're going to plug in 4. So 3 plus negative 1 to the power of 4. What's negative 1 to the power of 4? Positive 1. 3 plus 1 would be 4. So our sequence here, our first 4 terms of the sequence would be 2, 4, 2, 4. Awesome. In example 3, it says to write an expression for the apparent nth term of each sequence. When we do this in 8.2 and 8.3, we're going to have formulas to make it a little bit easier for us to come up with a expression. But for now, we're just going to kind of use our brain. So my terms for A, I'll do A over here, are 1, 3, 5, and 7. I'm going to make a little table here. So our first term is 1, our second term is 2, our third term is 5, and our fourth term is 7. What am I doing when I go from one term to the next? When I go from 1 to 3, from 3 to 5, 5 to 7, what are we doing? We're adding 2 each time. When we add a constant number, this is kind of like the slope of our equation. So it's kind of in the form of y equals mx plus b a little bit. Now, when we do this in 8.2, we're going to have formulas. It's going to make it a lot easier for us to come up with the examples. But for now, we're going to think about it this way. What do you think our slope would be? What are we increasing by to get from one number to the next? 2. Instead of x, we're going to use n because n just tells us it's the number of terms. And then to find b, that's going to be our starting number. Now we need to be careful here because b isn't where our first term is, it's where our 0 term is. So let's say instead of starting at the first term, we started at the 0 term. What would my 0 term be? What would I need to do if I go backwards? What do we think? Subtract 2. Awesome. If we're going backwards, we subtract 2. So 1 minus 2 would be negative 1. So our b, our 0 term, would be minus 1. So this would be our equation of our sequence here. And instead of y, we name our sequence by a sub n. That way I could plug in whatever number I wanted it into n and get that term. If I plugged in 2, let's say I wanted to find the second term. 2 times 2 would be 4, minus 1 was 3, which is exactly what we have for our second term there. So this would be our expression for the sequence. Again, when we do 8.2, we're going to have a formula. It's going to be a lot easier for us to just plug things in, but for now, we're just getting an idea, an introduction to our sequences. Let's do B. So our first term is 2, our second term is 5, our third term is 10, and our fourth term is 17. Am I adding the same number to get from one term to the next here? No, we are not. Do we notice any other pattern that's happening here? Let's think about it. What if I squared each of my terms? If I said 1 squared, what would I get? 1. If I said 2 squared, what would I get? 4. If I said 3 squared, what would we get? 9. And 4 squared? 16. What's the difference between the numbers that I wrote on top and my actual terms? They're 1 less, or my actual terms would be 1 more. So I could write my expression here as n to the power of 2, because n is our number of terms. I took 1 to the power of 2, 2 to the power of 2, 3 to the power of 2, 4 to the power of 2, and then just add 1 to it. So this would be my expression. A sub n is equal to n squared plus 1. So for this section, we're just recognizing the patterns. In example 4, we're going to talk about a recursive sequence. So a recursive sequence involves not only the number of term that we're looking for, but the number before that, the term before that. So we want to write the first 5 terms of the sequence. It gives us a sub 1. A sub 1 is equal to 3. That was given. In order to find the next term, we have to use the first term. Let's say I wanted to find a sub 2. If I plugged 2 into my k here, I'm looking for a sub 2, the second term. We would have 2a sub 2 minus 1 plus 1. What is a sub 2 minus 1? What's 2 minus 1? 1. So this is a sub 1. So what it's asking us to find a sub 2, we need to do 2 times a sub 1. What is a sub 1? 3 plus 1. So when we plug in 3, we have 2 times 3 plus 1 would be 7. To find our next term, a sub 3, if I were to plug in 3 into here, to find a sub 3, we have 2 times a sub 3 minus 1. So now we're looking for a sub 2. We're using a sub 2 plus 1. What was a sub 2? 7. So we're going to take the term before and use that. So 2 times 7 would be 14 plus 1 is 15. Then to find a sub 4, we have 2 times, what do you think I'm multiplying here? What would I use here?
A sub 3.
A sub 3, which is 15. Perfect. We used the term before, so 2 times 15 would be 30, plus 1 would be 31. And then lastly, since it asked us for the first 5 terms, we got to find a sub 5. So 2 times, what would I plug in here? 31. 2 times 31 would be 62, plus 1 is 63. So our first 5 terms would be 3, 7, 15, 31, and 63. So for a recursive sequence, or anytime you see that k minus 1 as our sub-interval there, or our that index there, we are looking for the term before to help us find the next one. We're going to skip example 5. And let's go down to factorial notation. So factorial notation is this exclamation point here. So it says n exclamation point, where the exclamation point means that we multiply that number and every number that comes before it. So if I had, let's say, 5 factorial, this would be 5 times 4 times 3 times 2 times 1. So that 5 exclamation point, that exclamation point is a factorial. We multiply that number and everything that comes before it. If I had 6 factorial, this would be 6 times 5 times 4 times 3 times 2 times 1. A couple important ones that I want to mention here is 0 factorial is 1, and also 1 factorial is 1. So 0 factorial is equal to 1, and 1 factorial is also equal to 1. So in example 6, we want to write the first 5 terms of the sequence given by a sub n is equal to 2 to the power of n divided by n factorial. Begin with n is equal to 0. So our first term we want to find is a sub 0. So what am I going to plug into the n's? 0. So 2 to the power of 0 over 0 factorial. What is 2 to the power of 0? 1. Awesome. And what is 0 factorial? 1. So 1 divided by 1 would be 1. Perfect. So our first term is 1. Let's find a sub 1 now. What am I plugging into the n's? 1. So 2 to the power of 1 over 1 factorial. What's 2 to the power of 1? 2. And what's 1 factorial? 1. So 2 divided by 1 is 2. Let's find a sub 2 next. So we're going to plug in 2 into the n's. So we have 2 to the second power over 2 factorial. What's 2 to the second power? 4. And then 2 factorial is 2 times 1, which would just be 2. So we get 4 over 2, which would simplify to 2. Then let's plug in 3. So 2 to the third power over 3 factorial. What is 2 to the third power? 8. Awesome. 3 factorial is 3 times 2 times 1. What's 3 times 2 times 1?
6.
So we get 8 over 6. What does 8 over 6 simplify to? 4 over 3.
4 over 3.
Because we divide them both by 2. And then let's find, we're looking for 5 terms. We've got 4 so far, so one more. A sub 4. 2 to the 4th power over 4 factorial. What is 2 to the 4th power? 16, perfect. 4 factorial is 4 times 3 times 2 times 1. What's 4 times 3 times 2 times 1? So 4 times 3 would be 12, times 2 would be 24. So we get 16 over 24, which would simplify to what? Awesome, 2/3. We can divide them both by 8. So our first 5 terms here would be 1, 2, 2, 4/3, 2/3. Let's look at A in the next example. So here we are simplifying our factorials. On top we have 8 factorial. So this is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, 2 factorial would be 2 times 1 times 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And we could just multiply all these together on the top and on the bottom and divide. But if we didn't have a calculator, we would definitely want to simplify first. We can cross out any common factors on the top and on the bottom. So we've got a 6 in common on top, 5, 4, 3, 2, and 1. So those would all cancel. Do we have anything else that would cancel? How many times does 2 go into 8? 4. So I can simplify a little bit more. I can cross out the 2 and the 8 and change the 8 to 4. So now what do I have left? I have a 4 and 7 on top, and then just the 1 on the bottom. So what's 4 times 7? 4 times 7 is 28. 28 over 1 would just be 28. So it's a lot easier to simplify than it would be to multiply them all together and then divide at the end. Another way that we could have done this is if I see that I have a 6 factorial on the bottom, I can simplify the 8 factorial or break it down until I get to 6. So let's say on top we had 8 times 7 times 6. I know from 6 down, it's going to cancel out with the 6 on the bottom. So I can just stop there and say 6 factorial over 2 times 1 times 6 factorial. So then from here, I know that the 6 factorials are going to cancel. So instead of writing it all out, if you see that you have the same thing on the bottom, you can just pause and cancel it out with the 1 on the bottom. And then here we would have 2 that goes into 8 4 times. So we have 4 times 7 on top, which is 28. So same answer. Just saves us a little bit of time writing it all out. Let's look at B. So B is the same idea, but instead of numbers, it has n's. But we're doing the same thing. On top, we have n factorial. So my first number would be n. How would I say 1 less than n for my next number that I multiply by? So how would I decrease this by 1 each time? The next number would be n minus 1. The next one would be n minus 2, and so on. It would keep going. We just would decrease by 1 more number each time. Over on the bottom, we have n minus 1. What do you think the next number would be? N minus 2, perfect, and so on. It would keep going. Do we see a pattern? Anything going to cancel? The n minus 1s are going to cancel, n minus 2, and everything else that comes after it, because it's just going to be the same thing. What do we have left? N. Awesome. So our answer would be n. On the last page, we're going to talk about summation notation or sigma notation. It is this E looking like symbol here. This summation tells us that we are finding the sum of all the numbers. So we would be plugging in from our lower limit at the bottom here, so 1, to our upper limit and every number in between, and we add up all of our terms together. So this is the sum. We're looking for the sum of everything, so that just means we add up all of our terms. So let's do A. So I want to start with my lower limit 1. I'm going to plug 1 into my I. When we plug in 1, we have 3 times 1, which would be 3. I'm going to plug in 1 all the way up until I get to my upper limit, which is 5. So I'm going to plug in 1, 2, 3, 4, and 5. So then we're going to plug in 2. We had 3 times 2, which would be 6. Then 3 times 3, which would be 9. Then 3 times 4, which is 12. And then 3 times 5, 15. Once we get to our upper limit, we stop. So we start with the lower limit, plug in this number first, and plug in everything in between the lower limit and the upper limit. From here, we're going to take all of our terms and we add them all together. 3 plus 6 is 9. 9 plus 9 would be 18. Plus 12 is 30. Plus 15 would be 30 plus 15 is 45. Awesome. So our answer would be 45. So we just add up all of our terms. The symbol summation means that we add. Let's look at B. What do you think I would start plugging in here? 3. We're going to start by plugging in our lower limit, which is 3. I'm going to plug in 3 and all the numbers in between 3 and 6. So 3, 4, 5, and 6. So starting with 3, we have 1 plus 3 squared. 3 squared is 9, plus 1 would be 10. Then 1 plus 4 squared. 4 squared is 16, plus 1 is 17. 1 plus 5 squared. 5 squared is 25, plus 1 is 26. And then lastly, we're going to plug in 6. 1 plus 6 squared. 36 plus 1 is 37. So then since we're looking for the summation, we're going to add up all of these numbers together. So I'm going to add the ones place first. 7 plus 7 is 14, plus 6 would be 20. 2 plus 1 is 3, plus 1 is 4, 5, 6, 7, 8, 9. So we should get 90. Any questions here? We're going to do one more just for fun. I'm going to call it C. Let's say we were looking for the summation from 1 to 5 of 4. What do you think we would do here? So in the last one, we would start with our lower limit. We'd start with 1 and plug that in. What am I plugging that into here? Do I have an I in my equation here to plug it in? No. So hypothetically, if we were plugging in 1, what would we get? We'd just get 4. I want to plug in 1 and every number from 1 to 5. So I'd plug in 2, 3, 4, and 5. If we plugged in 2, what would we get? We would just get 4 again. We're not plugging in anything, so we're not changing the outcome. Our function is just 4. So we'd get 4 each time. If I plugged in 3, what would we get? 4. If I plugged in 4, what would we get? 4. If I plugged in 5, what would we get? 4. So when we add up all of these together, 4 plus 4 plus 4 plus 4 plus 4, we would get 20. So there's some questions on the WebAssign. If it doesn't have an I to plug into, it's just a constant function, your outcome would be whatever the number is there. So then you would just have to add up however many of those you have.